Okay. Thank you. Thanks for organizers to giving me this valuable opportunity to be here and share our recent work. And at the beginning of this talk, I would like to invite you to quickly think about the serpentinite and fault behavior. I guess most answer could be like fault creep or slip seismically. But in this work, we will prove like earthquake rupture can propagate in serpentinite. We got some evidence from the 2023 magnitude 7.6 Elbistan earthquake in Turkey. The typical example about the serpentinite and the fault creep should be the Hollister Parkfield section of the St. Andrews Fault, where the creep rate is very high, larger than 20 millimeters per year. Back to the 1940s, geologists already promoted that the serpentinite distributed in this section as these green patches in this figure may contribute to the high creep rate along this section. After this section, along with the disappearance of serpentinite, the creep rate decreased very quickly. By using the samples collected from the drilling for Safford, Moore and Ryman observed the tackle in the sheared serpentinite has sufficiently low friction, which could allow the fault creep. And based on the high velocity friction experiment on serpentinite, Coley mentioned discovered that although when at the seismic slip, the serpentinite will behave as a velocity strengthening, but when at the seismic slip rate, the serpentinite could be changed to active as dynamic weakening, which means it could facilitate the rupture to propagate. This is a beautiful example of the serpentinite shear room along the Livingstone Fault in New Zealand. They observed Charling did a detailed field investigation of this serpentinite shear zone. They observed pervasively foliated serpentinite with more competent material reports, and they also observed this kind of straight and polished fault surfaces, which locally covered by this magnetite. Then they collect samples from this kind of fault surface. Then they observed different serpentinite inclusions with distinct petrology and microstructures, showing as a dehydration sequence. Then they interpret this kind of sequence to has occurring because of the co-seismic thermal pulse or propagation. Then they successfully used the phyllite element model to testify their interpretation. So there still has many other experiments focused on the velocity weakening of serpentinite. Some of them and this kind of numerical model supported like serpentinite is supposed to enable rupture propagation. So, but to date, we still didn't find any surface rupture has been documented in nature. This is other beautiful example is the 2004 magnitude 6 Parkfield earthquake. The field investigation find that the surface rupture propagated toward the northwest, and then it met the serpentinite region. But somehow the surface rupture didn't choose to broke through the boundary between the serpentinite and the mudstone. Instead of just directly cut through in the serpentinite. So still, until now, we didn't find any any evidence, any seismic rupture propagate into the serpentinite. But here, our work can prove this. So I guess most of you probably already familiar with the 2023 Turkey earthquake. On February 6, two earthquakes struck the region of Turkey and Syria. The first one and caused catastrophic death and widespread damage. The first one, magnitude 7.8, just struck the East Antonia Fault. After 9 hours later, the second one struck the Chardok Circle Fault. To the west of this fault, the rupture just unexpectedly branched off to the northeastern direction and along the Daigosha Fault. After this earthquake, USGS quickly mapped this surface rupture. These are a good one, but from their mapping, we can still have some mapping gaps, as these blue lines shown here, especially along the northeastern striking of the second earthquake. Then Florian used the Sentinel-2 images to acquire the deformation field with 10 meters resolution. They used this deformation field, mapped the surface rupture in January, and recognized some geometrical complexities. But they also did some measurements. Based on their results, they find the all-fault deformation of the second earthquake could be around 47%. And we noticed that to the northeastern section of the second earthquake, they got the almost 100% of the all-fault deformation. We speculated this extremely high all-fault deformation could be caused of their lack of the high resolution close to the fault. Thanks to CNES, during the last year, we continually got the high resolution images, including spot images with resolution 1.6 meters and players images with resolution of 1.5 meters. With these images, we use optical image correlation method to process them to acquire the high resolution displacement map. The key to this method is to rectify these images and to calculate the earthquake-induced movement of the scene pixel in pre-earthquake images and post-earthquake images. And then we acquired the 1.6 meters horizontal deformation fields of the second earthquake. In this study, I only focus on the 60 kilometers long section, but since our high resolution data only covered the area with a width of 5 to 7 kilometers, we to better constrain the deformation caused by the second earthquake, we also processed the Sentinel-2 images, and then we merged them together to finally get the 1.6 meters resolution cosmic deformation field. During the process of the images, processing of these images, we got the auto-rectified images and the DMs, which can help us to firstly doing the detailed surface rupture mapping, as this red line shows here, and also I replenished this Dangish fault, which showing as these white lines, which hasn't been documented in previous study. From our detailed mapping, we can recognize the 5 large-scale geometrical complexities from west to east is GC1 to GC5. For instance, the GC1 is the most complicated one. I call it a complex double band. And this 3D view shows, from this 3D view, we can see there have like 3 faults with localized deformation and 2 diffused area with all fault deformation. And yes, I also did many measurements, including on total displacement and on fault displacement measurements, also the deformation width. I extracted the long profile and used the long linear regression far from the fault to measure the total displacement. And with short linear regression, less than 200 meters to get the on-fault deformation. Then we determine the off-fault deformation by using the total displacement minus the on-fault displacement. This figure shows our displacement measurements along the fault. These blue circles are our total displacement, and these red squares and crosses are our on-fault displacement. From this measurement, we can say our total displacement decreased from about 6 meters at the west of GC1 to about 3 meters at the GC2. Then the total displacement just generally constant at about 3 meters toward the northeast, with locally increased to maybe about 4 meters at GC4. To the end of the rupture, the displacement decreased to about 1.5 meters. We also compared our measurements with the previous study. We can say the amplitude and the spatial variation of our total displacement almost align well with the results from Floria, who used the 10 meters displacement measurement. And our own fault displacement are consistent with the field measurements did by these two groups. Then we calculate the all-fault deformation, which is showing as this green area. From our calculation of the all-fault deformation, we can say on the eastern striking section, the all-fault deformation is about 34%, but to the west it increased a little bit. Along the northeastern striking is about 52%. Previous study already emphasized that the strong connection between the all-fault deformation and the geometrical complexities. The most recent study by Ji Hong also supported this. And I guess maybe some of you already talked to him with his study. In this, here we find the strong correlation between the geometrical complexity and the all-fault deformation maybe only exists to the west of the section. I mean, we can say GC1 and GC2 they get the high all-fault deformation, but to the west, go on along the northeast striking section, we can say before the surface rupture arrived at GC3, the all-fault deformation already changed a lot. So especially at the GC4, we can see the all-fault deformation almost close to 100%. And the GC2, the all-fault deformation between GC2 and GC4 increased to 65%. So we wanted to ask, why does the major increase in all-fault deformation on this northeastern striking section not directly align with the geometrical complexities? We then speculate that maybe the lithology probably controls the all-fault deformation in this area. We combined the geological maps with our surface rupture mapping. From this combination, we can see at the beginning, the surface rupture almost follows the geological boundary, like between the different limestone, between the schist and the limestone, between the granite and the limestone. But from the point A, the surface rupture began to propagate into these greenish patches, which is buried metamorphic ophiolite complex. First, the rupture propagated into this light green area, which mainly include serpentinite, and then it goes into the dark green area, which also have locally distributed serpentinite. So based on this combination with we combination the lithology and our all-fault deformation distribution, we think the lithology transition correlates well with the location where the all-fault deformation and even the deformation width start to increase. Even there's no obvious geometrical complexity nearby. So until now, we demonstrated that the earthquake rupture can successfully propagate through the serpentinite, and the serpentinite can strongly impact the core seismic deformation distribution. But how? We wanted to find more. Then we went back to check the displacement profiles, wanted to, especially those profiles in serpentinite region, trying to find more details about the deformation. So we first compare the profiles, one in regular rocks and the other one in serpentinite, as shown here, AA prime and BB prime. Then we can see from the AA prime, we can see quite a typical localized deformation with very well recognized steps. And then, in contrast, it's not obvious to find the localized deformation on the BB prime. Even we smoothed a little bit about the profile, we only can see those small steps and this slip gradient. So, so the localized deformation is much smaller than on A prime, even although they have the similar total displacement of around 4 meters. Then I checked more profiles in serpentinite, and we can see the similar patterns with those very small steps and this kind of slip gradient. So we can so the deformation in this serpentinite region is actually partitioned between these subparallel narrow bands, either with localized deformation or or the distributed deformation. So we then try to find explanations for this deformation pattern in serpentinite. I'm still using the serpentinite shear zone of the Livingstone fault to as an example, because this is a very beautiful one. And from a macroscopic view, the observed massive serpentinite, scaly serpentinite with a lot of distributed rhodingite ports in this serpentinite. They observed some SC fabrics, and we can see the quite clear faulted rhodingite ports. On the other hand, René also collected the serpentinite samples at the Monterey County, California, which is in the section of in the creeping section. They observed the distributed deformation with the SC fabric was cut and or separated by this kind of dark gauge material where it has a localized deformation. So based on these macroscopic and microscopic observations of serpentinite region in previous study, combined with our new observation in this study, we proposed this model to interpret the different deformation patterns in the serpentinite region and the regular rocks. We conclude that the heterogeneity of serpentinite rich shear zone could play a crucial rules in rupture propagation and accompany increased of fault deformation. In contrast, the rupture in the regular rocks may only accompany less of fault deformation with a lateral deformation zone. So this study is probably the first time in nature we observed the serpentinite rupture propagating into or through the serpentinite region and induced abnormally large fault deformation. So I know it would be better to go to the field to have more detailed observations of this region, but we didn't find the opportunity to get there last year. And I think we will plan to go there, do detailed observations maybe the next month. Yeah. So we hope that can happen. This is some conclusions. Okay, that's all my talk. Thank you very much.